Okay, thank you. Thank you for the invitation, and very happy birthday to Spenta, Rajesh, and all the ICTS family. I'm really heartened to see that this is one set of people, despite not having any computer scientists around, they really want to engage, and I really hope that next time I'm here in a few years, for the next important milestone, we have a thriving community of computer scientists. So I'm going to talk about a topic which is very recent, which is about bias, and also very controversial. And I hope I can give you a viewpoint, a mathematical viewpoint of what it entails, how bias emerges from the so-called objective world of mathematics and algorithms, and how we will have to develop a new set of techniques, algorithmic techniques, mathematical techniques, which would have to be based on a variety of considerations involving humans to counter the effects of bias. So I guess today it's not a big secret that our lives are surrounded by a variety of algorithms. In pretty much any task that we want to do today, we rely on applications such as Google, Facebook, even personalized medicine, Uber, and whatever. So algorithms are really, and these applications are driven by algorithms, and they are really touching our lives like never before. Well, a rather sad thing that is emerging is what is being called algorithmic bias, or the bias emerging from the deployment of these applications. So let me give you a few examples. So here's an example of a beauty contest which was judged by an artificial intelligence algorithm, and it made a strong correlation between skin color and beauty. I guess many people are probably aware about the bias, the racial bias that emerged, at least in the US, where algorithms were used to determine who gets bail and who doesn't. And I guess then there is this experience that we have about how the world around us is polarizing. And here you see a simulation by Wall Street Journal about feeds on different feeds of different users, one of our left and one of our right, on the same worldview. So bias across political opinion. And then, of course, the traditional bias, which also exists in our society against gender, is also showing up rather starkly on various online settings. So women are consistently shown ads by Google, which are for low-paying jobs. And if you look at Google image search, it consistently misrepresents the percentage of women in various professions. So So why do we care about all this bias? I mean, at the end, it's just out there. So the reason why we care about this is because studies are showing now that what we see online affects our perceptions, affects the ground truth itself. So a study by K. Matushak and Munsun showed how seeing distorted results on online search can distort people's view on what the ground truth is. A study by Epstein and Robertson showed that by showing people different information, they can manipulate election results. And also, a study by Garimella and others shows concretely the polarization on Twitter networks. So the bias is also affecting our society, and hence there is a great need to address and understand these problems. So at the core of many of these problems that I talked about, for instance, the beauty contest one, or the deciding who to give bail, or selecting a sample, they all rely on solving some or the other fundamental computational problem. And these are words, but they are all different problems in the context of computer science. And algorithms for these problems have been deployed. So let me give you an example of how the choices that an algorithm designer makes can result in bias or can promote societal biases and bring them into the world of algorithms. So consider the example of deciding who to give a bank loan. So the real world consists of a huge set of people, and there's a bank which is trying to decide on what criteria should I give a person a loan or not. So this is a so-called classification problem. So the starting point of many of these algorithms is to start with a data set. So this data set consists of a subsample of the real world, a bunch of peoples, which are represented typically as in some geometric space. Here, there is an x-axis and there is a y-axis. If you like, you can imagine the x-axis corresponds to the income and the y-axis corresponds to education. So they are both increasing in these two directions. And and the data points in these settings typically also have certain sensitive attributes. For instance, here it is gender. Now, if you look at the society today, this is not a very surprising picture. For whatever reasons, women do tend to have lower incomes, and they do tend to be lesser educated. Now, why it is the case, I'm not going to address that, but this is not. I mean, this is how a typical picture will look like if you collect data from the real world. And what is it that an algorithm would like to do? So the algorithm is trying to find how to decide, how to find a criteria, how to divide the set of points into two parts, one to which we give the loan and one to which we don't give the loan. So here comes the problem of model selection. How to choose, how to divide the space. Simplest possible way you can think of is to draw a line across this plane which cuts the set of people into two parts. And this is one of the choices that an algorithm makes. What is this set of objects that I need to search over to cut the data set? And once you decide this model or the class of models, you also have to provide, as an algorithm designer, with a metric which measures how good a particular point in this class of models is. So this gives rise to a certain utility function or a metric which measures the quality of a solution. So for instance, here, it's a very simple bifurcation of this space, which is based primarily on income. So the bank could decide that I want to find a threshold for an income for which I'll give loan to people who are above this threshold and people who are below this threshold. Now here in this very simple setting, you can see that because of the bias that already existed in society against women, this creeps in if we use this rule. Okay? So you may ask, okay, maybe use another rule. And okay, so I mean, one important point here is that these decisions that we make algorithmically, who to give loan and who to not give loan, will further affect the state of the particular sensitive class. So this is why this is important, to cut down this feedback loop, which can really drive the world to extremities. So you could ask for other possibilities, and maybe here is another line which divides the people into two parts. Now here, you can count that the number of men and the number of women who do not get the loan are same. But then this kind of a line is unfair, as somebody may argue, against an individual. An individual who is well educated and has high income might be not given a loan just to ensure some kind of a fairness. So there is really no way out of this. In fact, John Kleinberg and his collaborators established a rather nice impossibility result that you cannot really have an algorithm or a definition which will work for all notions of fairness. So this is not something that we can hope. And so the question that arises is, how do we define fairness? do we expect a single definition of fairness, or do we expect 5 definitions of fairness, or do we expect a definition of fairness which depends on the context? And the answer is the latter. So we are going to present a definition of fairness, which is, rather than being a definition, is just a framework, provides you a language to encode fairness constraints, and it is powerful enough for you to be able to express any constraint of your choice, and at the same time it's simple enough to be mathematically tractable. So an observation here is that the issue of bias or fairness arises in these settings primarily because data, so you have to select some subset of the data, and so imagine that your data consists of different types. So these could be divided on gender, these could be divided on race, these could be divided on political opinion, and so on. So there are different groups, and suppose you select this particular subset of this group of the data, then the number that seems to show up in almost any metric that you would define is the probability, Pi, that an item from a particular group Gi is selected. And in fact, all fairness metrics, as far as I can think, can be expressed as some function of these numbers, Pi's. So once you fix the set S, you get these numbers Pi's, and then you encode then you write down a metric or a function of these Pi's. And then you try to optimize or control fairness with respect to that particular metric. So our approach is rather simple. We consider the following kinds of constraints, where for each group, we would like these Pi to be at least something and at most something. So there's a lower bound and there's an upper bound. And these lower and upper bounds are the parameters of the algorithm. So there is a choice that the person who's using these algorithms has to set these. So I'm not going to give you proof of this, but it can be shown that these set of constraints are simple, convex, but also general enough to encode a very large class of functions over these probabilities. So what are the challenges once we have this framework? So there are 2 challenges. One is how to decide these parameters, how to find these parameters, how to find these groups. And the second challenge is, assuming these groups and parameters, how do we design new fair algorithms in this setting? And the first one is rather an interdisciplinary effort. I must say that I'm not qualified to address that problem. So I'm going to focus on the second challenge, which is assuming that we are given these parameters, how to design fair algorithms. And we have done experiments, real experiments, where we show also in the case of a variety of real settings how we can often deduce parameters. But ideally, one would have a kind of a different theory as to how to set parameters in our model. Okay, so I'm going to focus on a very particular problem of data summarization, or rather diverse data summarization, something that you all have done and Google does all the time. You go to Google Images, you search for the word scientist, and Google, from its billions of images which correspond to scientists, has to select a subset to show to you on the screen or your mobile phone, which is rather small. So it tries to solve the following problem, where you want to find a diverse subset. And the notion of diversity is not defined here. So I'll tell you one definition of it in the next slide. But roughly, the idea is, the problem that one would like to solve here is that there is some function f, which is, let's say, a non-negative function defined on subsets of this data set, and you would like to output a set S with probability proportional to this. So in terms of measures of diversity, typically these images or documents or whatever kind of collection of objects that you deal with on the web, the first thing machine learning people do is to convert them into some kind of feature vectors. So there are some black box algorithms, black box for me, I don't understand what is going on there, but they do seem to convert images to vectors. And now, so the mathematical problem becomes how to define a measure on subsets of vectors. So you give me a bunch of vectors, what are natural measures on these vectors which give you a sense of diversity for a subset. So let's look at this matrix, which is an M cross D matrix. M is the total number of vectors, and D is the dimension in which the data points sit. And the matrix you think of as a rectangular matrix. And so suppose you have a subset of vectors, and then you look at the corresponding submatrix where you pick the columns corresponding to the set S. Then one measure is the following. So you look at these vectors, you look at the parallelopipe formed by these vectors, and you take the squared volume of that. And this has a rather nice mathematical expression, which is the determinant of this matrix Vs transpose Vs. So I did not come up with this measure. This is a very popular measure in machine learning, and it has been used for a variety of data. And it also shows up in a variety of mathematical and physics areas. It's called the determinantal point process. So this is a natural object, and we will see why working with this gives rise to nice mathematical problems that we can try to solve. So the data also has attributes. So in this case, there's gender, male, female, and one thing that I'm not going to convince you right now, but you can. I can show you experiments offline that just sampling with respect to this measure does not seem to have much correlation with gender, diversity, and so on. So a combinatorial measure of diversity would be something which is spread out in this combinatorial space. This is a geometric measure of diversity, and they don't seem to be compatible. So as a consequence, we go back to our framework where we choose to enforce these constraints, and we would like to solve the following computational problem. That I give you a bunch of vectors, V1 to Vm, which is partitioned into sensitive classes. So here it's based on gender, male and female. And I also give you numbers, k1 and k2, which are integers, positive integers. And I would like you to pick a set S, which picks exactly ki elements from each group, such that the measure is supported only on sets which satisfy this property. So the probability that you pick a set S when restricted to sets that satisfy this property is the same as what was before, and it's 0 if a set doesn't satisfy this property. Okay? So these are called DPPs, or determinantal point processes with combinatorial constraints. And more generally, or more abstractly, you can imagine that I give you a family of subsets B, which you think of as fair sets, and your goal is to solve the following computational problem. And here it becomes important that the set B is given to you implicitly. Okay, because we want, so in computer science there's often a notion of how the input is given to you. These sets are exponentially sized, I cannot list them, otherwise efficiency will reduce to triviality. So I have to give you a succinct way to describe this family B. So DPPs actually have a very nice and intimate connection with polynomials, which I'm going to show you in this slide. So if you look at the generating polynomial of the DPP measure, which is really just writing down the determinant of this thing here times the monomial, which correspond to the product of variables in that set. This has a very succinct formula in terms of a determinant. Okay? And where this capital X is the diagonal of these variables. So you construct a diagonal matrix where you put xi's in the diagonal. And the sampling problem, okay, so there is a nice result from computer science from the 80s, which says that sampling is efficiently equivalent to counting. What this means is that the task of picking a set S from this probability distribution is the same as the computing this partition function. This was a result proved by Jerome Valiant and Vazirani. And using this now, you can see that if I want to sample from the unconstrained DPP distribution, it is the same as a single evaluation of this determinant, which is efficient. The DPPs come with an efficient algorithm. Now, what about this fair counting problem, where we are given a subset and we would only like to extract the sum of coefficients of the polynomial corresponding to this family B? Now, this turns out to be immediately very hard. In fact, you can show that you can very easily encode the problem called the permanent in this framework. And permanent is a notoriously hard problem which was proved to be so by Leslie Valiant in 1984. So here is a polynomial. This is not the permanent. This is just a polynomial which you can see requires you a very small circuit to compute. It's just a product of certain number of linear forms. And if I ask you what is the coefficient of the monomial which corresponds to the product of all the variables, you recover exactly the permanent. And hence, even the simplest case where I give you this family B as a single point, it becomes very hard. So problem is even harder than permanent. It ends up being related to, very intimately related to this mathematical object called mixed discriminant. So this is a generalization of the permanent involving matrices, and importantly, it showed up in these recent proofs of this Cadison-Singer problem. And in fact, our results show that if you could solve these problems even reasonably approximately, you would make these proofs constructive. So we don't know how to do this. So the question that we would ask is, can we solve this counting problem approximately, given the hardness? And an object that plays a role here is so-called the polytope of this family B, where for every set S in this family, we think of it as a vector where the coordinates of the vector indicate whether a particular element is present or not. And you look at the convex hull of these points, we assume that we are given a way to separate over this polytope, which means that if I give you a point, either tell me it's in the polytope or produce a hyperplane separating the point and this polytope. So we wrote down a rather strange looking analytic expression, which is an optimization problem over this polytope, and proved that it gives a reasonably good approximation to this quantity, this partition function, when this family B corresponds to what is called a matroid. And in fact, we realized that our proofs only use the fact that the polynomial is real stable. This is the generalization of something called real rootedness for univariate polynomials. And roughly it means that the roots of the polynomial P do not lie in a certain region of the complex plane. So that's all we needed, and that's a property satisfied by these determinantal polynomials. So that helped us. Now the question of computing or optimizing over this is rather intricate, and turns out to be related to the so-called computing maximum entropy distributions. So what do I mean by that? So I mean, I guess if you're familiar with the second law of thermodynamics, you might have seen this in disguise. So here, the problem can be reformulated as the following: that I give you, so find a point theta, so that if you write this as a convex combination of the vertices, then the entropy is maximized, and then find a point which maximizes even this entropy. Okay? So we want to find such a point in this polytope. That's really what this relaxation is doing, and we can show that we can compute this. And the resulting convex program has applications far beyond what we originally imagined, and that's one of the messages, I guess, I would like to, we are searching for problems in various domains and making connections which are unsuspected. Okay, so to summarize, I would like to point out that we presented a general framework to understand and define fairness. We developed algorithms for one particular problem, which we call data summarization. And it has led to a variety of unrelated consequences in belief propagation, probability, computing the so-called Braskamp leap constants, and so on. Entropy is the key thing that connects everything here. And so beyond data summarization, we also have some work on ranking, on personalization. This is something that you experience on Facebook. And also multi-winner voting rules, which are used in selecting committees and so on. So we have different, so these problems are different, the algorithms that you need are different, and maybe some other day I have more time to talk about some of them. So going ahead, I guess the key set of problems that seem to be important in the setting are how do we detect bias and how do we set parameters. So ideally, we would like that there is some automatic way of detecting bias, detecting communities, setting parameters so that the algorithms can be what I would like to call self-healing algorithms, that they can correct their biases, detect and correct biases all the time. We are very far from this. Closer to reality are things like studying the impact of these fair algorithms on users, understanding how much utility do we lose when we impose these constraints, and also talk to companies and lawyers in trying to understand how we can deploy this in the current legal and business framework. So we have started some dialogues and also build some products which I can share with you if you're interested. And beyond bias, I guess there are many other issues that are showing up. The notion of accountability, transparency, and then what is truth, something that David talked about. So overall, we see that in this emerging area, there are many challenges that are being presented for which I believe will require a unity of a variety of sciences to address, not just mathematical sciences. And this is what ICTS is all about. So here is again wishing you a happy 10th birthday. Thank you.
Thank you, Nisheeth, for a very nice talk. You can take questions.
Nisheeth, you used lack of bias and fairness interchangeably. I just wanted to know if that is completely clear. And the second question is, in all these cases, the notion is extrinsic, and is there a completely intrinsic notion of bias and fairness, or do you have to specify based on some other higher principles that are outside of the data set you're looking at?
The first question is much easier to answer. So yes, I did use them interchangeably. The second question, I'm not sure. I mean, bias is a relative thing, you know, so it's not something that I would consider is intrinsic. So in a sense, okay, if you fix a certain type of dynamics, if you fix a certain type of algorithm, if you fix data, then it becomes intrinsic to that particular setup. But to define extrinsic, we have to probably define what it means, what is outside the system and what is inside the system. So I didn't give a good answer to your question.
Yeah. The bias thing that you showed, where you drew a line to separate two data points, like the women and the men there. So when the mixing is a bit difficult to draw a straight line, what if I could bend the plane on which I'm plotting the points, probably convert it into a homeomorphic plane, where instead of a curved line splitting it into two data sets, I could draw a straight line. Like, would that kind of approach to separate data points be much easier?
So that people use in machine learning, it's called kernel methods, roughly. And what you do is you transform your vectors into in a certain manner so that curves become straight lines.
Okay.
So in some sense, straight lines are general enough here.
Oh, thank you.
Yeah.
Okay. On the polyhedral combinatorics sort of formulation you had with this, you said that something comes down to a matroid structure.
Yeah.
What is that separation oracle some sort of a matroid optimized?
Yeah, so we need a separation oracle for matroid polytopes, but we know that.
Polymatroid, right?
Yeah, not
Sure.
polymatroid, just simple matroids. Yeah. So things like partition matroids or spanning tree polytopes and matching. I mean, the matching is not an example, but yeah, so we need the separation oracle for these polytopes.
If we were living in a malicious world,
Yeah.
then we might want to maximize unfairness and maximize bias. Is that going to come out of your algorithms very easily just by reversing the sign here? So
Yes.
you can maximize unfairness and bias and all?
Absolutely. In
Yeah.
fact, these algorithms can all be used to control people's opinions.
Okay.
Yes. But I believe they're already being used. So this is a way to provide citizens the ability to control the information they're seeing. A lot of these methods are probably being used to manipulate people's opinions.
How does the general population understand it's unfair? And we don't present the separating hyperplanes. We tell them a story which they'll believe. Is there any theory about this?
So banks will, of course, never tell you how they decide whether to give you a loan or not, I guess. And that's where I talked about accountability. You know, there should be more regulations for entities to declare how they are making decisions in advance. I mean, working at a university, and being in various committees, we often decide who to hire, who not to hire. We really don't have any explicit written down rules which we can put out in the front, right? So we use criteria, and sometimes we try to justify. So we are not very different from banks when it comes to certain things. Of course, banks control our money. Yeah. Yeah.
Okay. There are these statistical paradoxes like the Simpsons paradox, where you have trends in groups of data that vanish or are completely reversed when you pool all the data together. Is this something that you worry about? Or
I'm sorry, could you explain yourself? Yeah.
there are these statistical paradoxes. I mean, one is called the Simpsons paradox, where you have certain trends in subgroups of the data that are completely reversed when you pool the data together. And this sort of raises issues of you may see bias if you look at subsets, but that bias vanishes when you look at the overall, when you group everything together. Is this something that you think about? Or?
I have not thought about it. That's an interesting thought, and I would probably talk to you offline about it.
Okay, so if there are no more questions, let's thank Nisheeth again, and let's also thank all the speakers of this wonderful session.